Hello and welcome to my talk about a performance-portable distributed k-nearest neighbors algorithm using locality-sensitive hashing and SYCL. My name is Marcel Breyer and I'm a PhD student at the University of Stuttgart in Germany in the Institute for Parallel and Distributed Systems in the Department Scientific Computing. At first, I want to give a short motivation why to use k-nearest neighbors algorithms. In the age of data collection, data mining is important, and data mining is the art of extracting information from huge data sets. And one such information could be the classification task, and that's the task of generalizing known structure to apply to new data. And one possible classifier is the k-nearest neighbors algorithm, as already proposed by Cover and Hart in 1967. The naive brute force k-nearest neighbors algorithm calculates the distances between the new data point and all other data points. However, this is infeasible for large data sets, so someone should use other algorithms to perform the k-nearest neighbor search, for example approximate algorithms. And approximate algorithms have the advantage that they do not need to calculate the distances to all other data points, but only to a subset of the data points. And one approximate k-nearest neighbors algorithm is locality-sensitive hashing. So at first, let me introduce you locality-sensitive hashing. Locality-sensitive hashing has been proposed by Indig and Motwani, and as the name suggests, it uses hash tables. So given a data set with data points in a high-dimensional space, they are at first mapped to the one-dimensional numbers line. And this mapping is done through hash functions, but not ordinary hash functions. Instead, locality-sensitive hash functions are used. And they have a special property. Given two data points, if the data points are close or similar to each other, they have the same hash value with high probability. However, if two data points are far away from each other, they have the same hash value only with a small probability. So now, the locality-sensitive hashing algorithm calculates these mappings for each data point. In this example, those three data points have the mapping value 1, and then the points are inserted into the hash table according to their mapping value. So those three data points are inserted into hash bucket 1. Now, if we want to calculate the nearest neighbor of this red data point, at first its mapping is calculated, which is 1. Then we look into hash bucket 1. And now, in order to calculate the nearest neighbor of this data point, the distances to all other data points in this hash bucket have to be calculated. So in this example, we can reduce the distance calculations to 2 from 5 if we would use the naive algorithm. However, locality-sensitive hashing has disadvantages. For example, it can happen that all data points are mapped to the same hash bucket because those hash functions are normally generated from random values. So if all data points are mapped to the same segment, they are inserted into the same hash bucket and no improvement compared to the naive algorithm can be achieved. So in order to prevent this, we not only use a single hash function to create this mapping, but we concatenate many hash functions to a hash signature, and we use this signature to sort those data points into the respective hash buckets. Another problem can arise if we look, for example, at this data point and want to calculate the nearest neighbor of this data point. At first, we calculate the mapping, which is 2. We look into hash bucket 2. Now we see no other data point resides in hash bucket 2, so we cannot calculate the nearest neighbor of this data point. To prevent this, we not only use a single hash table, but multiple hash tables. And then, for example, in the first hash table, the data points are inserted like this. But in a second hash table, this data point is mapped to segment 3. Now this data point is inserted into hash bucket 3 alongside this data point, and now the nearest neighbors of those two data points can be calculated. Up until now, I have talked about locality-sensitive hash functions, and now let's have a closer look at such hash functions. At first, the random projections as proposed by Datar et al. Given the previous dataset, at first we have to calculate a mapping from the high-dimensional space to the numbers line. using a scalar product and an addition. The entries of the vector A are independently chosen from the normal distribution, and the scalar B is chosen uniformly at random from the interval 0 to W. After that, our numbers line is divided into segments of the same size. And now the final hash value is calculated by looking to which segment the data point has been mapped to, and this can be done through an integer division of the segment size W. The random projections have two advantages. At first, creating the hash functions is efficient since we only have to draw d+1 random numbers, and calculating the hash value is efficient too, since we only have to calculate a single scalar product, an addition, and an integer division. However, a disadvantage is that not all segments have the same number of data points. So for example, segment 0 has 0 data points, while segment 1 has 3 data points, resulting in a load imbalance if we later want to calculate the nearest neighbors for all data points. Another type of locality-sensitive hash functions are the entropy-based hash functions as proposed by Wang et al. Given the same data points, at first we have to calculate an initial mapping using a scalar product where A is again chosen from the normal distribution. And then we have to introduce a new hyperparameter R, and R represents the number of segments we want to have at the end. So we have 3 segments, and the idea is that each segment has the same number of data points. So in this example, given 6 data points, each segment should have 2 data points at the end. In order to calculate those segments, we have to get those cutoff points. And if we have those cutoff points, calculating the final hash value is easy using a simple lookup function. So the advantages of entropy-based hash functions is that calculating the final hash value is efficient since we only have to perform a single scalar product and a lookup. And now we have a better load balance since each segment has the same number of data points. However, this time creating the entropy-based hash functions is more inefficient since in order to get those cutoff points, we have to calculate the mappings for each data point and then sort those mappings globally. While sorting is rather costly, sorting in a distributed system is even more costly. Since I wanted to implement a performance-portable locality-sensitive hashing algorithm, I now want to talk about SYCL, a framework which allows someone to achieve performance portability. At first, what is SYCL? SYCL is a cross-platform abstraction layer for heterogeneous computing, and therefore it can target a variety of different hardware platforms, being it CPUs or GPUs or FPGAs or special vector units from different vendors. While SYCL 1.2.1 built explicitly on top of OpenCL, SYCL 2020 allows the usage of other backends like nvidia's CUDA, AMD's ROCm, or Intel's Level 0. SYCL tries to combine the concepts, portability, and efficiency of standards like OpenCL with the ease of use of modern C++. This allows us to use C++ constructs like templates or inheritance inside SYCL kernels. However, other C++ constructs like exceptions or virtual functions are not allowed inside kernels. Additionally, SYCL is based on a single-source multiple compiler passes architecture. That means that in one pass, a host compiler can compile the host code, and in a second pass, the device compiler can compile the kernel codes. This allows the user to lift the restriction of physically separating the host and kernel code into different source files. But why would you need something like SYCL? For example, here we have 4 supercomputers. AMD's Frontier supercomputer will consist of AMD CPUs and AMD GPUs. Perlmutter will consist of AMD CPUs and nvidia GPUs, while Intel's supercomputer Aurora will consist of Intel CPUs and Intel GPUs, and the HPC5 supercomputer consists of Intel CPUs and nvidia GPUs. As we can see, 4 supercomputers with 4 different hardware configurations. Now, as a developer, it would be nice if we only would need to write a single program to target all 4 supercomputers with reasonable performance, which can be achieved using SYCL. SYCL is a standard developed by the Kronos Working Group, and currently many different SYCL implementations exist. For example, mainly developed at Intel, DPC++ is part of the OneAPI initiative. It can target Intel hardware and nvidia GPUs using cuda PTX as contribution from CodePlay. CodePlay itself developed Compute CPP, which can target any CPU, Intel hardware, AMD GPUs or ARM Mali GPUs. Additionally, it can target nvidia GPUs using OpenCL and PDX. However, the support for nvidia GPUs has been discontinued recently. TriSYCL sees itself as testbed for new SYCL features. It can target any CPU using OpenMP, and since it is mainly developed at Xilinx, it can also target Xilinx FPGAs. HipSYCL is developed at the University of Heidelberg. It can target any CPU using OpenMP as TriSYCL, and it can target nvidia GPUs directly using cuda and AMD GPUs directly using ROCm, and therefore it's currently the only implementation not relying on OpenCL as backend. Additionally, recently it also introduced support for Intel GPUs using OpenCL and Intel's Level 0. The newest SYCL implementation is NeoSYCL, developed at the University of Tohoku. It supports Intel CPUs and special NAC vector units. This now brings me to my implementation. The goal of my work was to implement an already known k-nearest neighbors algorithm, namely locality-sensitive hashing, on a possible distributed system using multiple GPUs, supporting potentially different vendors, hence the usage of SYCL. For example, here we have 3 GPUs. Now, at the time I started to work on this project, HipSYCL had a runtime restriction that allowed me to only spawn a single SYCL queue per host thread. Therefore, I had to be a bit tricky to support multiple GPUs. So I spawned 1 MPI process per GPU, although, for example, those 3 GPUs could reside on a single compute node. Then I have 1 big binary data file and I read it using MPI-IO, and each MPI rank reads its part of the complete dataset and directly copies it onto device. Then the hash tables and hash functions are calculated. Afterward, the initially empty k-nearest neighbors are copied onto the device, updated using the generated hash tables and the dataset, and then copied back to the host. Now I have preliminary KNN calculated. However, in order to get the final KNN, those KNN have to be compared to a part of this part of the total dataset and a part of this part of the total dataset. So I have implemented a ring-like communication pattern based on multiple rounds. Since every KNN has to be compared to the other data parts of the datasets, in total we need, if we use 3 GPUs, 3 rounds to calculate the final nearest neighbors. So in each round, 1 MPI rank receives the part of the dataset from its previous rank, copies it onto device, and asynchronously sends it to the next MPI rank using another STD thread to hide communication and computation. Additionally, the KNN from the previous MPI rank are received, copied to the device, then updated using the received part of the dataset, the previously generated hash tables and the read part of the dataset, and then copied back to the host and sent to the next MPI rank. After all rounds, in this case 3, have been finished, the final k-nearest neighbors are calculated. which now leads me to my results. At first, my setup. I have compared 3 SYCL implementations, namely Compute CPP, HIP-SYCL, and TB-C++, on a single node system using 8 NVIDIA GeForce 1080 Ti's, and DP-C++ on a single node system using an Intel Iris Xe Max GPU. Unfortunately, due to hardware limitations, it was only possible to get results on a single node system. Additionally, I've used 2 datasets, the Friedman dataset consisting of 500,000 data points in 10 dimensions, and the Higgs dataset consisting of 1 million points in 27 dimensions, which is a real-world dataset. Additionally, I've implemented different evaluation metrics. At first, the recall, which is the ratio of the true positives and the relevant elements. However, the recall is a hard metric, since in an approximate algorithm it can be sufficient to get nearest neighbors that are not the exact nearest neighbors, but that are relatively close to the exact nearest neighbors. But this would still result in a bad recall. Therefore, I've also implemented the error ratio, which is the ratio of the distances of the calculated nearest neighbors and the correct nearest neighbors. And this now takes into account that calculated nearest neighbors that are not the exact ones but extremely close to the exact ones are still good enough for an approximate algorithm. Additionally, to show the scalability of my algorithm, I've also plotted the parallel speedup using 1 GPU up to p GPUs. At first, we have a look at a random projections hash functions using the Friedman dataset. Each data point represents the runtime for the creation of the hash functions and hash tables and the k-nearest neighbors calculation if not stated otherwise. And each dot represents one specific parameter set averaged over multiple runs. As we can see, increasing the recall increases the runtime. Up until recall of 20%, the runtime does not increase. However, afterwards the runtime increases drastically when approaching 100% recall. We can also see that all 3 SYCL implementations on the same hardware have the same runtimes. The only outlier being DP-C++ on the Iris Xe Max GPU, which is arguably slower than the NVIDIA GPU. Looking at the error ratio, achieving an error ratio of 1.0 equals achieving a recall of 100%. Therefore, while approaching an error ratio of 1.0, the runtime increases drastically. However, if an error ratio of 1.3 or 1.4 is sufficient, the runtimes for all 3 SYCL implementations on the NVIDIA GPU already drop below 1 second, and afterward they won't increase or decrease even for a worse error ratio. Now switching to the entropy-based hash functions, again with the Friedman dataset, we can see that the overall runtime characteristics are the same. Increasing the recall drastically increases the runtimes. However, this time, even though the same hardware is used, HIP-SYCL, DP-C++, and Compute CPP do not have the same runtime characteristics, because Compute CPP and DP-C++ both have a high static overhead of 6 and more than 10 seconds. This is caused by the creation of a SYCL queue inside the constructor of the entropy-based hash functions. However, I don't know why both SYCL implementations have such a high static overhead, especially since DP-C++ using the Iris Xe Max GPU does not have such a high overhead. Looking at the error ratio, we again see the static overheads, and that the runtimes drastically increase when reaching an error ratio of 1.0. And again, increasing the error ratio after 1.3 does not increase or decrease the runtimes anymore. Now, if we ignore the runtimes for the hash function creation and therefore ignore the static overhead, we see that All three SYCL implementations on the same hardware have again the same runtimes for the recall and the error ratio. And now, if an error ratio of 1.3 or 1.4 is enough, our runtimes consistently drop below 1 second for all three SYCL implementations. Next, I've plotted the parallel speedup using up to 8 NVIDIA GeForce 1080 Ti GPUs using Compute CPP and HIPSYCL as SYCL implementations and the Friedman and Higgs dataset. At first, for the random projections, using the Friedman dataset, both SYCL implementations scale up to 6 GPUs, but the parallel speedup is bad, with a parallel speedup of not even 3 using Compute CPP and 4 using HIPSYCL. However, if I use the Higgs dataset, both parallel speedups improve significantly. HIPSYCL now has a parallel speedup of nearly 7. However, again, Compute CPP scales worse compared to HIPSYCL. Looking at the entropy-based hash functions and Compute CPP using the Friedman dataset, we see that it doesn't scale at all. Using 8 GPUs has no runtime benefit compared to using only 1 GPU. Using HIPSYCL and the Friedman dataset starts to scale. However, a parallel speedup of nearly 3 is still very bad. Now switching to the Higgs dataset, Compute CPP scales a bit better, but is even worse than HIPSYCL with the Friedman dataset. And now HIPSYCL with the Higgs dataset has a parallel speedup of up to 6. This bad parallel speedup is caused by the fact that Compute CPP has the static overhead in the constructor of the hash functions, and that the creation of the entropy-based hash functions involves a global sort. And currently this sort is only implemented using a modified distributed bubble sort algorithm, which isn't quite sophisticated. However, if we again ignore the runtimes for the entropy-based hash function creation step, we now see that even when using the Friedman dataset, the entropy-based hash functions now scale on up to 7 GPUs and scale better than the random projections. And now using the Higgs dataset, HIPSYCL even has a parallel speedup of nearly 8. But again, Compute CPP has a worse parallel speedup across all tests compared to HIPSYCL. In order to explain that, I have plotted the runtimes for the respective rounds, as I mentioned in the implementation section. We have 8 GPUs, therefore to calculate the final nearest neighbors, we have to perform 8 rounds. And now, as we can see, HIPSYCL has less overhead when invoking small kernels. They need approximately 50 milliseconds less runtime. Even when using the Higgs dataset, HIPSYCL has less overhead compared to Compute CPP, which can be explained by the fact that HIPSYCL directly uses cuda, while Compute CPP is based on OpenCL. This now brings me to my conclusion. As we have seen, better recalls and error ratios increase the runtime. However, if smaller recalls or bigger error ratios are sufficient, as often in approximate algorithms, the runtime decreases drastically. The locality-sensitive hashing algorithm has many hyperparameters that can be tuned, and they can be tuned such that a target recall of 60% can be achieved with the drastic decrease in the runtime. My results for the random projections and entropy-based hash functions were overall comparable. However, the entropy-based hash functions can further be refined using a better distributed sorting algorithm, and the entropy-based hash functions, compared to the random projections, needed less hash tables in order to achieve a comparable recall, and therefore needed less memory on the GPU, resulting in the possibility of processing even bigger datasets. Additionally, I have shown that my implementation easily scales on multiple GPUs with a parallel speedup of up to 7 when using 8 GPUs. However, I've also shown that HIP-SYCL scales better than compute CPP because of a smaller static overhead for short kernel invocations due to the direct use of cuda compared to OpenCL. And the runtime characteristics are similar for all three SYCL implementations, compute CPP, HIP-SYCL, and DPC++, with the only exception being compute CPP and DPC++ when using the entropy-based hash functions and the nvidia GPUs due to the construction of the SYCL queue inside the hash function creation step. For further reading, I've provided additional sources for the k-nearest neighbors as classifier or locality-sensitive hashing with the two implemented locality-sensitive hash functions, and a relatively new book about SYCL using DPC++. That's from my side. Thank you for listening to my talk and have a nice day.